Okay, let's, there's all sorts of challenges to do here. Here, let's just do this one. Here's another cell. Here's your equation. It's all balanced for you. You need to identify what all of these letters represent. And if you want to on the bottom, you can also diagram what the cell looks like. Here we're just identifying the parts. So what's this metal in A? What's the metal in B? You have to look it up here. You can figure out which one's the anode and which one's the cathode. Although here, let's do convention. Let's say that we're going to have the anode on this side and the cathode on this side. I'll tell you that. And then you figure out the rest.
NIBR? So crazy.
All right, so like I said, this one is really just practice. Make sure you understand when you interpret a figure like this, you know what all the parts are. Right? You might see a problem that you're given this and you have to identify things, or you might see something in reverse. You're shown everything and you have to identify what's this, what's that, what's the other. Or be able to identify it from the shorthand, right? We won't have time to go through all of those examples, but I think there's examples like that in the homework for everything. So first, we need to figure out what's being oxidized and what's being reduced. So let's just take a look at that. We've got silver and we have gold. So what's happening to the silver? Is it being oxidized or reduced? It's being oxidized. So that's going to be, now of course this is in the direction that's written. We don't know if it's spontaneous yet. So we have to figure out, really, if we're going to identify what's the cathode and what's the anode, we need to first know what direction this reaction is going in. All right? So maybe this was easy, maybe this wasn't easy. Depends on how it was set up. So if that's being oxidized, that means the gold is being reduced. As written, let's take a look at what the reduction potentials tell us. When they're both being reduced, which one has the greater reduction potential? The gold or the silver? The gold does. So gold has the largest reduction potential, so this one will be reduced, meaning that this one will be oxidized. That's what we've discovered up here. So in fact, yes, this reaction does run in the direction that it's written in. Right? But you've got to check. You have to check that. Okay, let's put that in red here. Must check see which direction is spontaneous. Not spot, spont. Right, now that we know that, we can label things. So the anode then is what? Is it silver or is it gold? The anode is where oxidation happens. That's going to be silver. So that's silver solid, which means that the cathode has to be the gold solid. So then what ions would be here in solution in C? What are we going to have? Silver plus ions. Will there be any other ions in solution? Remember, we have that in aqueous solution. So we're also going to have sodium ions and we're going to have nitrate ions. All right, and then in D, the ions that we'll have then are going to be the gold 3+, and we'll also have the sodium ions and the nitrate ions. But yes, what we're really concerned about here is the ions of silver and the ions of gold, where they're going to be. All right, so salt bridge, we know what's going on then in the salt bridge. Which ion is going to go from left to right? Do we know that yet, or should we figure out where the electrons are going first? Let's figure out where the electrons are going first. So the silver is being oxidized. So are the electrons going from left to right, or are they going from right to left? They're going from left to right. I'm not even going to say how many electrons are flowing. They're going this way. So what then in the salt bridge is moving from left to right? Is it the sodium ions or the nitrate ions? The sodium ions, because you want to neutralize the charge. And the nitrate ions are going this way because you're replenishing the negative charge that was left, that was leaving the cell. Okay? And we can answer the other questions that aren't on here, but that we've been practicing with. What's E naught of the cell going to be? What's E naught of the cell? It's going to be whatever the reduction potential is minus the reduction potential of the thing that got oxidized. And that minus, right, that operation basically reverses the reaction for it, right? It reverses the reduction potential. So what's that going to be? It's 1.4 minus 0.8, which is 0.60 volts. Do you want to calculate delta G? How do you calculate delta G? We need to know how many moles of electrons are transferred in this reaction. Can you tell by just looking at it? It's 3. You have to balance the redox you have to balance the half reactions, but that's an easy one to balance because as written, actually, it's already balanced for you because we have 3 silvers go to 3 silver pluses. That means 3 electrons were transferred here. And 1 gold 3 plus goes to 1 gold solid. That's also 3 electrons. So this is 3 times, let's see if I can get it right. Let's see, 9.65 times 10 to the 4th coulombs multiplied by 0.60 volts. And that will give you whatever that answer is. You want to get it in kilojoules per mole, of course. This is per mole of reaction. If we were to hook this up to a voltmeter, this box at the top, what would it read? Would it read this value?
In kilojoules per mole.
173.7. So what's going to be shown up on this voltmeter apparatus that you're going to use in lab on Monday? Is it going to be minus 173.7? It'll be positive 1 point, whatever you said? No, that's not the right answer either. What's going to show up in that box?
Voltage?
Voltage. What's the voltage? All right. This is going to read plus 0.60 volts. And if it reads negative 0.60 volts, what does that mean? It means the way you hooked it up is non-spontaneous. So you have to switch the electrodes. Okay. The magnitude will be the same. All right. Shall we diagram this one too? The anode. So what's the metal of the anode? Silver. Turning into silver plus. And then on the cathode side, we have gold 3 plus going to gold solid. Let's put all of our states of matter here. Okay? See if you can solve this one. Calculate E naught for the cell. You have to look at your table. You have to interpret this shorthand, and you have 5 answer choices. Be proud, be proud. You shouldn't have to do too much to solve this problem. So in fact, I'm going to stop you now, because if you're still working on it, that may mean that you're going the wrong way about it, or you're doing too much to figure this out. Take a look at this reaction, and even if you don't remember what's on the left and what's on the right, you can tell that you've got reduction and oxidation happening between 2 metals. One of them is nickel, and the other one is silver. So you have to just look at the table. What's the reduction potential for nickel? What is it? You all looked this up, right? Negative 0. What? 256?
Yes.
7. Okay. And what's the reduction potential for silver? We just did that one, right? Plus 0.800, right? So, if we set up a cell with these two metals, one's going to be the anode, one's going to be the cathode, right? The cathode is where reduction happens. That's going to be determined by which one is going to get reduced from these two. Which one will get reduced in competition? Which one's
The silver.
The silver, thank you. This one's going to get reduced, which means this one gets oxidized. So E naught of the cell is simply going to be whatever gets reduced, because that's what the reduction potential tells us, minus whatever is being oxidized, the reduction potential of the thing that gets oxidized. That's of the nickel, that's negative 0.257. That's going to equal plus 1.06 volts. So the answer is 1. Okay, that's how you would approach a problem like this. Here's a short list from the table. All right. So given these are all standard reduction potentials, that's what this is here. If we mix solid aluminum with a 1 molar solution of tin 4, I'm not telling you what the spectator is, all right? Tin 4 cations. What have we asked for here? Oh, will it react? If we mix solid aluminum and tin 4, will it react? What do you think? What do you want to be thinking about here? If it reacts, what happens? It means something gets oxidized and something gets reduced. Show of hands. Who thinks it will react? Who thinks it won't react? Why? Why? Why does it react? How do you know? What's the thought process? Who wants to give it a shot? That sounds good, right? Where the materials were, tin 4 plus and aluminum solid. And if it's going to react, that means that the aluminum solid is going to go in reverse to form aluminum 3 plus, and the tin 4 plus is going to go as written to form, in this case, tin 2 plus. It won't go all the way to tin solid, right? And how do we evaluate that? Well, what's the reduction potential for each one? The reduction potential, if we just mix tin if we mix tin 2 plus and aluminum solid with each other, you just go by the one that has the largest value for the reduction potential. That means that, yes, this will go this way, which means it will force the aluminum solid to go in reverse. That will react. Okay? Do the same thing now with this last one. Will solid tin react with a 1 molar solution of iron 2 plus? What do you think? Will it react? Who thinks it will react? Who thinks it won't react? Let's take a look at what we have going on here. So now we're looking at tin solid, which is here, and iron 2 plus, which is here. So when we look at this table, right, if we react solid tin with iron 2 plus, well, will this actually, let me rephrase that. When we put solid tin and iron 2 plus together, will they react, right? And the answer is no, because the tin is already in its reduced form if you were to set these up in competition, right? If we were to set up tin 2 plus and iron 2 plus in competition with each other and ask which one's going to be reduced and which one's going to be oxidized, the one that gets reduced will be the tin 2 plus to tin solid, because that has the higher reduction potential. So it's already happened. It won't go in reverse. That's why the answer is no. Here, let's start with some of this practice here. Here's the question. Given the following reduction half reactions, what will be the overall net reaction value of E naught of the cell? Now you're given two half reactions, both in the reduction form, right? And you're given what the reduction potentials are here. You need to use these values. What's going to be the overall net reaction? This looks really, really complicated, but if you know what you're looking for, it's actually a very, very fast, easy question. Let me just reemphasize, that's the correct solution. That's the correct fast solution. There are harder ways to solve this problem, but just take a look at these two reactions. One of them is going to be oxidized and one of them is going to be reduced. The one that's going to be reduced is going to be the one with the highest reduction potential. That's going to be the cobalt 3 plus goes to cobalt 2 plus. So this one's going to be reduced, meaning that we're going to use that reduction potential, plus 1.92 volts, which means that this one has to be oxidized. It's going to run in reverse. So that means we're going to have negative 1.36 volts here, and we subtract those two together, add them together. This adds up to 0.56 volts. And there's only one answer choice that gives us the right E naught of the cell. Now, if you take a look at this answer, it's also balanced. Okay? Because it's also balanced for the number of electrons. And you could have done it that way. You still need to know which direction it's going. You still need to know which one's being oxidized and which one's being reduced. Now, remember that even though it's balanced, E naught of the cell stays the same. Because remember, that's the voltage drop, right? The voltage potential doesn't change. It's what we call an intensive property of the cell. Its value stays the same regardless of what you're doing. What affects the work that you can get out of it, that's the charge, delta G, that's going to be based on the flow of electrons. Delta G is equal to NF E naught of the cell. And for that, we'd have to know how many moles of electrons would actually be flowing through this cell. How many moles of electrons? What would N be in this case? It's 2. We have 2 electrons here, we have 1 electron there. We'll have to balance the number of electrons. The lowest common multiple is 2. If we did it that way, we would end up with these coefficients. Right, so we have 2 moles of electrons are transferred. Here's some more practice interpreting the shorthand. Now this one's a little trickier because you have to pay attention to what's solid, what's an ion, and it's aluminum and silver, so one's Ag and one's Al, and it's hard to see everything, right? But just look carefully. Which is the correct cell diagram for a cell constructed using a spontaneous reaction? So you know, if it's spontaneous, you know that this reaction is going in this direction. Therefore, you should know what's being oxidized and what's being reduced. And you have to remember, what's the convention? Well, actually, I'll ask you that when you're done solving it. Once again, we'll put number choices here. 1, 2, 3, 4, 5. Okay, who has an answer? Good. And number? Which number is it? It's number 5. Right? Once again, if you practice this stuff, you should be able to get an answer like this very, very quickly. You need to know what the convention is. Right? When we have this shorthand, this is always going to be the anode side, and this is going to be the cathode side. And we start with metals, and then those metals go into ions in aqueous solution. Now, not all of these are easy, okay? But I try to give you the straightforward, easy ones because we're not going that deep into chapter 17 at all. So the other thing you need to do then is look at this spontaneous reaction and decide what's being oxidized and what's being reduced. Here, aluminum solid is going to aluminum. You don't even need to know what the charge state is, really, because you can see that aluminum is in an ionic compound. What is the charge state of aluminum here? In aluminum nitrate?
+3.
+3. So is aluminum being oxidized or reduced? Being oxidized. So we know that the start of our cell has to be aluminum solid, goes to aluminum 3+ in aqueous solution. And then you're pretty much done, although it's always good to double check. There's only, there's nitrate, but the nitrate isn't changing. The nitrate's just a spectator ion here. Here we have 3 silver ions. This is going to be silver 1+, is going to 3 silver solids. So we have, the electrons are balanced, 3 moles of electrons. This is going to be our silver plus in aqueous solution, and then the solid is the silver solid, which matches this answer choice here. So again, once you know what the conventions are and you practice this stuff, it's not that difficult. This is pretty much more of the same. Let's just do the top one. Magnesium solid plus, what is HNO3? What is that? Say it loud, I heard it.
Nitric acid.
Nitric acid, is that a strong or a weak acid?
Strong acid.
Strong acid. Not that it matters for this problem, but I'm just checking. You'll need to know this for the final exam. All right, let's identify what's being oxidized, what's being reduced, and how many electrons are transferred. Let's just do this one. We can do this one together. What's being oxidized? You've got so many choices. You've got manganese solid. You've got HNO. Here, actually, let's not even do it that way. Let's do H+ in aqueous solution. Let's do NO3- in aqueous solution. Let's do H2 gas. And finally, let's do magnesium plus in aqueous solution. What's being oxidized? 1, 2, 3, 4, or 5? One is being oxidized. The magnesium is being oxidized. This is magnesium 2+. You know that several ways. You know how to read it off the periodic table, or you notice that it's paired with 2 nitrate ions in aqueous solution in an ionic pair. Right? They need to be neutral. And then what's being reduced? Is it the nitrate or is it the hydrogen? What's being reduced? The hydrogen's being reduced. The nitrate ions are 1-, which means here hydrogen plus, and here hydrogen as a gas, that's neutral. So all the hydrogens are neutral. Yeah. How many moles of electrons are transferred? How do we find out? Look at the half reactions. Magnesium solid goes to magnesium 2+ plus 2 electrons. Now what about the hydrogens? We had 2 hydrogens, so they'll pick up 2 electrons to give us 1 mole of H2 gas. Of course, it helps when the equation is already balanced for you.